Welcome everybody to our senior design final presentation. We are team C49 Smart Home IoT. My name is Nick Ardetto. I'm the team manager.
I'm Jacob Common, computer engineer.
I'm Matthew Petter, computer engineer.
I'm David Keene, electrical engineer.
I'm Andy Yuan, I'm electrical engineer.
I'm Xingjian Zhao, I'm electrical engineer.
So just going over a few of our key talking points. First, I'm going to talk about our project overview, give you a little bit of information about how our product works and how their user uses it. Next, we're going to talk about the overall product design and talk about some of the choices that we made over the course of the past 2 semesters. Next, we're going to talk about the project deliverables. We're going to talk about how our validation of product success and how basically we tested our product for voltage and current in our server and our application tests. And then lastly, we're going to talk about our conclusions, hit on the areas of success, things that went well over the past 2 semesters. Next, we're going to talk about the areas for improvement, things that didn't go well. And if another team were to pick up where we left off, we can talk about future improvement for them. So for a project objective, our device is a power analytic device. It basically gives you the user information for the energy efficiency of their device. So our product is a custom PCB, a server, and an application. So the user will take our product, our custom PCB, plug it into the wall, and then plug a load into it, such as a toaster or an electric tea kettle. And then from there, our sensors on the board will determine voltage and current. And then our microcontroller will determine the power usage. And then that data will be sent over the Wi-Fi module to our server. And then that data will be calculated over a set amount of time to give a cost amount. That data is sent to the application via Android app. And then from the Android app, they can determine if the product is energy efficient or not. So they can choose whether they want to continue using the device or not.
So the goal for this device is to deliver comprehensive data presented in a comprehensible way on a per device basis. Power metrics isn't always the most intuitive thing to the average person, as you can see by this graph. Most people don't look at energy consumption on a graph like this, so why should the user have to? The analytics on this device are easy to understand, yet still provide useful information that tells the whole story. It can also suggest if the device being used is considerably more energy intensive and compared to similar devices. Via the app, it can also toggle that device on or off. So for some final design specifications, our goal is to deliver powerful data delivered in a compact, affordable device. The PCB allows for individual devices to be put on a small design, which is consistent with customer appeal. We use KiCad, which is an open source PCB design environment interface that was used to develop this PCB. The Android app allows for the general public to easily use that information at the touch of a button in their pockets. The server is hosted on a Raspberry Pi MySQL server. The hard drive mirroring serves as a storage hub to hold the database, and the integrated processors handle the data and perform the necessary calculations to provide accurate power usage readings. So here's a list of comparable designs in this field. There are various price points with various capabilities as well as different styles. Our price point in particular is more competitive as well as sleek enough to sit seamlessly in a customer's household.
So anytime you're developing a product, it is important to ask who we're trying to sell this product to. This influences not only how the product itself is designed, but also how it is marketed to the general public. It is important to have a project that customers find useful and will want to use often. We set out to develop a product that once the user has it, they continue to use it and be very satisfied with their purchase. Many people nowadays are much more environmentally conscious and are attempting to save as much money as possible, but are very uninformed about the electricity usage of their products. With this product, the user will have access to all the information they need displayed in an easy to understand way. That way, someone with no knowledge of power usage whatsoever will be able to identify where they are losing money. People don't often realize how much power their products are using, even when they're not on. Using this knowledge, customers will not only save money, but will also be more energy conscious, which is a big selling point for our product.
Here's the summary of the components. So we're using total 5 independent components on our object. The first one is a CS712 current sensor, which can measure the current from the appliance. And the second one is ZMPT101B voltage sensor, which can measure the AC voltage from the wall. And the third one would be the Wi-Fi module, which allow our product online and sending data to our database. The first one, for the power adaptation, we decided to use the 120 volt AC to 5 volt DC voltage step down module, since it's small and compact compared to other similar modules, and it has very good stability. For the last component, we do need a microcontroller, so we picked Arduino Nano to do all kind of stuff such as analyze and sending all the data, as well as communicate with the Wi-Fi module. And Arduino Nano is tiny, easy, and powerful, which would be the best fit for our product.
All right, so we're going to be looking at the Smart Home IoT power meter, which will deliver power metrics from sensors on the board. So right now, I'm going to plug in the load first, which is a tea kettle. We should be expecting something in the range of 12 amps or so, and now we will plug in the mains voltage to power on the board. We'll check the current reading with a clamp meter. So as we turn on, we're seeing 12.13 amps, and we will verify that data with the Arduino serial monitor. As for voltages, we're currently seeing 120.6 volts coming from the mains outlet, and we will check back in with the reported readings from the serial monitor. So as the Arduino serial monitor is reporting, we are seeing 119 volts RMS and 12.36 amps of current running through the load. The multimeter over here showing voltage is reporting 120.9 volts, and the clamp meter over here is reporting 12.22. It is multiplied by a factor of 10 for accuracy. So on the physical PCB itself, we have a variety of different components. Mains voltage is coming in through this terminal, and it will be powering the 120 volt AC to 5 volt DC step down flyback converter, which is used to supply power to the small electronics on board, which are the current sensor, the voltage sensor, the ESP Wi-Fi module, and the Arduino Nano microcontroller. This microcontroller is essentially the brains of the device, where it does all the mathematical processing and all of the analytical data that will convert the Arduino code into usable values that we can understand as humans, as it appears on the Arduino serial monitor. So from a hardware perspective, this board is pretty simple. Each of the devices on board have their own separate tasks. This would be the current sensor, which is measuring the current, obviously, as is the voltage sensor measuring the voltage. The ESP chip over here is the Wi-Fi module, which gets information from the Arduino Nano to send to the server that we have been using. And these two components essentially communicate all of the necessary information that is given by these two sensors to make use to the end user. So here's a look at the bottom side of the printed circuit board. Right here is the voltage sensor, which is measuring the parallel voltage at this node. Over here is where the current sensor is, measuring series current. In between those is the 120 to 5 volt step-down converter, powering all the small electronics on the board. These 8 connections right here are the pins for the ESP Wi-Fi module, which is communicating with the server and the Arduino Nano, which is all of the rest of these connections right here. All these connections have been soldered, and the PCB is complete. So in light of current events, we did not have access to a 3D printer to print off an enclosure for this device, but it's something that we had designed and would love to include in future developments.
So for the technical design, here's our custom PCB. And on the right side, we are going to run the 120 volt AC through the board, maximum 15 amps with 10 degrees Celsius temperature rise. For safety issues, we separate the 120 volt AC and 5 volt DC so that it won't cause any issues if they're too close to each other. And we need to make sure the copper thickness is good enough to handle the 120 volt AC. And we also have a test pin for the final testing. These two pictures are our custom PCB. As we may see, that the trace width on the right-hand side of picture 1 is way wider than them on the left. As I mentioned on the last slide, we need to make sure the 120 volt AC won't burn our board. By using the trace width calculator, we decided to use 3.3 millimeter trace width for the 120 volt AC and a regular 0.25 millimeter for 5 volt DC. We choose to put our voltage step-down module in between the sensors so that we may easily test and measure the current and voltage either in series or in parallel.
As far as software specifications are concerned, we have 2 main components. The first is Android Studio, which we use to develop the Android phone application. The second is Arduino IDE, which we use to download code to our Arduino Nano that will enable our components to work properly together. Our Android Studio's app's main purpose is to easily show the user power analytics of their appliances plugged into our wall outlet. Our app is connected to the server where the data is stored. The 3 main pieces of information that the app displays are the total wattage used, the total monthly cost based on the power used, and a graph which shows the power usage of your appliance over time. Our Arduino code initializes each individual component so they are working properly. And then the Arduino simply reads the values provided by the voltage and current sensors every second and sends those values to the Wi-Fi module. The Wi-Fi module, which is connected to the internet, sends data to our server to be stored. Lastly, our database, which is described further on the next slide, is using a Raspberry Pi and is being programmed using PHP. All the individual components are working as expected, but unfortunately, due to the coronavirus making things much more challenging, they aren't properly working together with each other.
As Matt mentioned in the previous slide, this is how our server works. It actually uses the MariaDB, which is an open source version of MySQL. With this MySQL, we use PHP myadmin to interface with the actual MySQL server. This is all done and ran on a Raspberry Pi 3 using the Raspbian Pi operating system. How the server actually works is that I wrote a PHP script that connects to the server and grabs data from the server. The Android Studio application then fetches this data. And then in order to connect the server to the internet, we actually had to forward port 80 on the router, as well as change the bind address on the Raspberry Pi. This sets up the IP address that the server should be listening on. I also set up a UFW firewall to allow traffic on the MySQL port. For testing purposes, it would have been a lot easier to implement the connectivity to the Android application by using the server on my base machine. For example, both the server and the Android application would be running on my MacBook. However, the goal was to keep the server remote because that is actually how databases work. So in the slide, you can see the top image on the left side is a screenshot of the PHP MyAdmin interface, where you can see different spots for our data. For example, the name of the user, the username, password, and the wattage that is supposed to be receiving from the Wi-Fi module. The picture below that is an example of our PHP script that is used to connect to the database. On the right-hand side is the output that is resulted from running that PHP script. So first, we know that it is able to connect to the server by being able to see the data that is in the actual database on the MySQL server.
So to validate some of the product success, we'll look at some of the electrical experimentations with it. The PCB design overall just ensures a compact board with safety and functionality being primary elements. The voltage and current sensor testing took two routes where we used two separate instruments to probe for both voltage both values. The digital multimeter probed for voltage at the wall, as well as checked at various points on the board, and a clamp meter with a 10 times line splitter measured current, which helped aid in current measurement as it was accurate to the 200 amps range on the instrument, and we could have more accurate readings from there. On the voltage sensor, there was also a potentiometer, which allowed us to dial voltages with respect to the experimental values from the tuned instruments. This allowed us to make sure that the voltage that we were measuring matched the voltage that was being seen by the load.
For the software experimentation, first we'll start with our firmware code. How our firmware code was tested was actually taking the outputs from the voltage and current sensor that Dave had metered and comparing them to the output code that was coming from the firmware. So whatever we saw in our console, we wanted to match that as accurately as possible from the multimeter readings. Next, with the firmware, we had to test our actual Wi-Fi module. This was done by using AT commands to see what messages are sent back to the Arduino. In one of the earlier slides, in the software specification slide, Matt was shown that one of the code shows that it was actually connected to Matt's phone. And then the next line shows a valid IP address. That means that the module had successfully connected to the internet. And as I kind of mentioned in the previous slide, the database is tested by running a PHP script to test if it can be actually connected to the database. If there is a connection, then the data will be displayed. As seen in the previous slide, this is the case. For the application functionality, this was tested by first being able to successfully launch the Android application and then being able to log in with a username and password. If this is successful, then the user should then be able to actively scroll through each screen. This meant, selecting which module you'd like to see, and then being able to see the data charts that are on the next screen. For our budget, we were fortunate enough to never have to run into any budget issues. That is because our overall spending was actually pretty inexpensive. This actually totaled out to be $52.86. One of the things we do notice is that when purchasing in bulk, for example, our custom PCB, when we purchase these components in bulk, this would actually drive the price down overall. So if we actually took this product to market and went into mass producing, then the overall budget would actually be driven down from this prototyping budget to an actual more marketable budget, as we propose to be $19.
For the areas of success, firstly, our hardware team successfully designed the PCB and built a prototype. It worked properly. Our Android app was well designed by our software team. Also, our server built on Raspberry Pi is capable of storing and transmitting data. The figure shows the error analysis of product. The error on the voltage measurement is 0.1%, and the error on the current measurement is about 3.4%, which is nearly neglectable. I also want to mention that it is a hard time during the current pandemic, and our team managed to keep making progress and finish our project. Overall, our design goal was relatively achieved. There are still some areas that we can improve. Firstly, we can design our own integrated circuit instead of using discrete sensor modules. That will also make our PCB cheaper and more compact. Secondly, it will be better if our product can measure more than one load and or appliances. Finally, we can try to reduce our budget. So for this project, we want to thank you to Dr. Ababe for many helpful guidance and assistance. And we want to thank Dr. Tama for the supervision and advice throughout COVID-19. And thank you to everyone who's helped us on this project.
Thanks everybody for joining us in our final presentation. If you have any questions, you can leave them in the comments. Appreciate it. Thanks.